The Tesla Model 2 is often misunderstood as a low-cost car with equally modest engineering. But Elon Musk has made it clear that this perception misses the mark entirely. Rather than producing a rushed budget vehicle, Tesla is pushing technological boundaries, crafting a compact car engineered for endurance, innovation, and long-term resilience, something designed not just for today but for the next 100 years. This isn't just about building an affordable EV, it's about redefining what a car at this price point can achieve. As Musk hinted, this isn't merely a revolution in vehicle design, it's a revolution in how vehicles are made. Hidden beneath its surface is technology that feels more at home in aerospace labs than automotive factories. The Model 2 represents a new standard, a synthesis of affordability and extraordinary engineering. This transformation begins with the core of the car's structural integrity. Beneath the unassuming frame lies the AstroLattice, a carbon fiber matrix. Adapted from the Crew Dragon capsule used by SpaceX, lighter than steel by 25%, yet 45% stronger. This innovation creates a safety shell with unmatched durability. This strength doesn't just protect occupants, it extends the car's range by optimizing weight distribution. The structure, verified through Tesla's 2025 aerospace-related patents, is not speculative hype, but documented and tested. Wrapping around this advanced material is the AstroLattice V2 frame, which eliminates traditional joints by casting the entire body shell in one solid piece. This one-shot casting process, blending liquid metal aluminum with polythermide fibers, produces a chassis that boasts torsional rigidity far exceeding the Model Y, and a vastly improved crash zone. While the AstroLattice frame costs significantly more, nearly $1,870 per unit, almost double the cost of a Model 3 frame. It's designed with no compromise in mind. Tesla's robotic gigapresses spray molten alloy at 3,200 degrees Fahrenheit to shape this body in under 2.5 minutes, more than doubling the time required in Model Y production, but delivering extraordinary precision. These industrial machines, consuming over a megawatt of power per cycle, operate with the force and finesse normally reserved for spacecraft. Tesla's internal simulations suggest that this frame may achieve a theoretical 6-star safety rating, pushing past the limits of traditional crash testing. Gigafactory Nevada now houses for such machines running in tandem, forming the beating heart of Tesla's next-generation vehicle architecture. The Model 2's structure alone is revolutionary, but its propulsion system is equally astonishing. The new drive unit centers on a T3 rotor magnet array complex, triple-layer motor with axial radial hybrid architecture and tungsten filaments. Each motor includes 19 pounds of tungsten, costing nearly $1,750 before even considering final assembly. The result is immense torques, 612 Nm, outpacing the Model 3 by 18% and increased thermal efficiency, sustaining performance even under extreme stress. In internal tests, peak output temperature dropped by 14 degrees Fahrenheit during prolonged runs, and the motor maintained continuous torque delivery over 7-hour cycles in the 105 degrees Fahrenheit heat of the Nevada desert. This isn't just automotive-grade durability, it's military-grade, reflecting Tesla's ambitions well beyond the consumer market. Tesla insiders reveal that this very motor architecture may form the backbone of the company's future autonomous freight systems, capable of powering hyper-durable, long-range electric cargo transports. It's no stretch to imagine that this motor, originally designed for aerospace and military-grade drones, is now being deployed in a so-called budget EV. Tesla is future-proofing the Model 2, not just in drivetrain durability, but in every aspect of its thermal resilience. One of the most unexpected features is the Model 2's 4D OmniShield, a thermal protection system derived from space mission tech. Built using graphene-based coolants and adaptive polymers, the shield allows the battery to operate between -60 degrees Fahrenheit and 160 degrees Fahrenheit. The Model 2 can maintain efficiency even in the most extreme environments, from icy Arctic terrain to scorching desert conditions, delivering a real-world range of 340 miles, where rival EVs drop significantly. While this thermal architecture costs an estimated $5,000 per unit due to proprietary materials and complexity, the results are unmatched. The battery's lifespan extends to 16 years, 30% longer than typical EV packs in the same class. Tesla's intent is clear: they're designing a car for real-world adversity, an all-terrain electric vehicle capable of handling the planet's toughest conditions. Beyond materials and motors, what may be the most shocking revelation is that Tesla has already manufactured hundreds of Model 2 units in secret, while speculation about its pricing and design swirled in public. Tesla was quietly building out a microfactory inside Gigafactory, Texas, known only by insiders as Spectre Lab. This hidden production line is ramping toward 3,000 units per month. By mid-2026, over 1,000 Model 2 South have already been built, logging more than 3 million miles across 6 continents in complete secrecy. These vehicles are reportedly operating under camouflage in isolated locations such as the Gobi Desert, gathering endurance and performance data without public attention. Engineers have dubbed this test fleet the Phantom Fleet, a silent army of disguised EVs feeding back intelligence from global roads before the public launch even begins. Tesla's strategy in keeping this hidden was simple: prevent competitive espionage. In markets like China, where companies like NIO dominate the EV sector, leaking early technical specifications could have triggered aggressive counter-engineering. Instead, Tesla took the stealth route, concealing test operations and deploying vehicles in areas difficult to monitor. This covert campaign is a powerful reminder of how Tesla treats new vehicle development, more like a military operation than a traditional manufacturing rollout. Inside the cabin and throughout the vehicle, Tesla has gone even further by incorporating materials once reserved for private jets and deep-sea research vessels. The so-called Neptunium alloy, a proprietary blend of titanium and vanadium, is the foundation of the Model 2's high-end interior. This alloy is 65% lighter than conventional steel and remains corrosion-proof for over 30 years, validated through aggressive salt fog and temperature cycling trials. It costs a staggering $4,500 per unit, or about 10% of the Model 2's projected price tag. Yet its benefits in durability and luxury are profound. While most vehicles offer interiors that degrade within 12 years, Tesla is offering a cockpit that can last 3 decades. The only limitation here is supply. Only 3 companies worldwide can produce Neptunium at the necessary purity level. As a result, production of the Model 2 is expected to cap at 110,000 units in its first year, regardless of demand. This cap effectively turns the Model 2 into a limited production luxury vehicle masquerading as an affordable compact. Tesla is targeting a new demographic with this move, not just cost-conscious consumers, but environmentally minded buyers with premium tastes, those who want luxury materials, long-term reliability, and sustainability all wrapped in one futuristic package. Even Tesla's manufacturing process reflects this commitment to bold innovation. While traditional automakers focus on lowering production costs to reduce prices, Tesla has flipped that logic entirely. They've implemented a new assembly architecture called the Blitz line, reducing build time from 18 hours for the Model 3 down to just 6 hours for the Model 2. This feat is achieved through a network of AI-powered swarm robots and pre-assembled vehicle modules. The entire Blitz line infrastructure cost Tesla over $1 billion, accounting for 13% of their 2025 capital expenditure. Instead of using this increased efficiency to lower prices, Tesla is reinvesting every dollar of saved cost into further improving vehicle performance, scale, and tech superiority. This efficiency allows Tesla to scale toward a production target of 2 million Model 2 units by 2027, with a long-term plan to capture 30% of the African EV market by 2030. That translates to a projected 4 million units annually. Tesla's strategy is clear. Instead of competing on price, dominate on capability, scale, and resilience. Every Model 2 sold not only funds the company's aggressive global expansion, but supports its deeper mission developing an autonomous EV fleet that could one day populate cities across the globe. When you step back and see the full picture, it's evident that the 2026 Tesla Model 2 isn't just a Carrizza statement, a bold claim that the future of automotive innovation doesn't need to come at the expense of affordability. Tesla has infused aerospace technology, deep-sea engineering, and revolutionary manufacturing into a vehicle that redefines what an entry-level EV can be. It's not cheap, and it's not compromised. It's a compact car wrapped in future-proof tech that borrows from the stars and the sea. If this vision catches on, the Model 2 won't just be remembered as Tesla's cheapest car, it'll be remembered as the car that changed everything.